On to our presenter today. Srinivasan is the chief data scientist at Cognizant and has 15 plus years of experience in building data-driven products for top financial customers. He is also experienced in building complex analytical pipelines, machine learning models for extremely complex business processes, petabyte scale data lake, and high frequency streaming analytics pipeline. He's also an YouTuber and runs a YouTube channel named AI Engineering where he covers all topics related to data. So without any further ado, handing over the stage to our presenter Srinivasan. Over to you, sir.
Yeah, thank you, Abhiraj, and thank you everyone for coming at this time. I know like there are people from multiple geography, and it's very late in India where most of the participants are. So let's get started. So in this video, in this webinar rather, I'm so used to taking YouTube videos. So, okay, in this webinar, I'm going to more focus on model deployment. Right, I'm going to talk about the challenges with model deployment. Typically, like how we think model deployment is, and how the real world model deployment looks like. What are the different components that need to come together to deploy a model in the production and integrate with your business process. So that is the key topic of this particular webinar. So let me quickly get started. Yeah. So about me, I think like Abhiraj gave a good introduction about me, while some may be overstated. So you can check me on LinkedIn. You can follow my post if you're looking for anything on data side of it. And I have a YouTube channel as well called AI Engineering. You can go and check my videos over there. So what's on the menu today? I know like a lot of people are waiting for their real menu. I'm standing in between their dinner time. But when it comes to like today's food for thought, I'm going to cover like complexity and challenges with model deployment. And then we are going to talk quickly about different options of deploying models. We always think like, okay, I have a model, I can just deploy it as a REST API and it will work. But there are a lot of other factors also comes into play. We will cover that. And what are the common mistakes to avoid when you are working in the enterprise trying to deploy the model? So that's about the coverage today. Let me get started. So how do most of us see model deployment? There are multiple reasons we see it that way, because we always think like the data comes to us in a single nice formatted CSV file. Or the other reason can be like that's what most of us have been taught, or the information is available online, right? What we think is I have a trained model and finally I have a model object. And the model object can be a pickle file if it's a scikit-learn, it can be a booster file. If it's an XGBoost, it can be a protobuf, it is TensorFlow. It can be a Mojo object if it is H2O, or it can be a PMML file, which is a common format for your model interchange, right? Now, this is what my model is. Okay, I can take it, I can Flask it, I can run it on a gRPC. Very rare cases, mostly people think like I can Flask it and my model is deployed and it's ready for inference, right? That's what we think about, like looks easy. But if it was that easy, why like there are so many failures in all the AI project? Like if you see the top 5 reasons AI project failed by all the Gartner reports and other research agency, you can see model deployment as one of the factors, right? And there are other things like data collection or data integration. The leadership knowledge also forms a pretty key factor, and the commitment can be an financial commitment or a non-financial commitment, even that can drive it. The availability of skills, and frankly, like today, I don't think skill availability is a major challenge. There are a lot of avenues where we can learn things. Yeah, there are some disconnect when we go to industry, but that can be caught up, right? And one other main reason is like the business team, the data scientist team, and the IT team are typically working in silos. There is no proper coordination, and until this coordination happens, deploying a model is a pretty big challenge. The reason is once the data scientist does an experiment, the model becomes a software engineering work, and the data engineers and the software engineers have to come together to deploy it. So these are some of the reasons. And if you really see like some of the research reports, what if you see over here, like many organizations have been developing machine learning models, but only 47% of those models make it into production. There is a other report by VentureBeat which says like even the AI piloting that is happening today. Uh, Out of all the successful AI pilots, when I say like successful, people have really found business value with their models. But those out of those successful AI pilots, only 30% to 40% are really able to go into production. So model deployment is one of the key challenge, and let's see like why that is a challenge, right? So let's see like how real world deployment looks like. What I'm going to do, rather than just running through a bunch of slides, I'm going to take a case study, and then I'm going to go with the case study and talk about how the pipeline looks like, how we are going to deploy it. And for this purpose, the business use case I have chosen is an typical retail industry problem, right? Yeah, the reduce the cart abandonment. So what is reduce cart abandonment? Like typically what happens in the retail industry, like customer go and add items to their shopping cart, and many people like do not check out the shopping cart, right? And that's where they are kind of abandoning their cart. Now if you see like kind of a country wise list over here, right, or a geography wise list, you have like Spain, which has the highest, it is 86% of carts are abandoned. And similarly, like if you see US, around 71% of the carts are abandoned. And this is like metrics coming from this particular website. You can go and cross verify as well. Now, what I'm going to do is I'm just going to talk about a US-based on online retailer, right? I'm just calling Amazing LLC. It has nothing to do with Amazon. It's just like a company, and their current cart abandonment is around 80%. Now let me go back and give an example. Take like case of Amazon and Walmart. They are kind of, the retail sales are in multi-billion dollars. So around like 50 to 60 billion dollars is the quarterly revenue. And even if they are able to reduce this 80% to 75%, they are literally adding around another few billion dollars to the revenue. The impact is so much. And not only that, they are literally enhancing the customer experience because they are helping the customer come online and complete their entire journey, right? So that is one of the key factors. So now this particular Amazing LLC has 80% cart abandonment rate, and the industry average is 72%. What I'm doing is I'm just framing the business problem. Let's get into the technology side of it pretty soon. Now, this particular retailer has tried all options, like provide a seamless checkout process, because that is one of the key factor, like customers drop out, right? You don't have a proper checkout process, proper payment option, or there's no increased transparency of the price. So sometimes when you add to the cart and finally go, you will see that there's a huge shipping cost available. So they have done all this, but still their kind of rate is around 80%. So what we are trying to do is we are trying to build an machine learning pipeline, which will try to reduce it by 3% by giving personalized offer. So we are going to see like what is the best offer we can give to this customer so that he can complete his checkout journey, right? And the business objective here is like convert the abandoned rate to the recovered ones, increase revenue and enhance customer experience. So now that we know the problem, now this is how my training architecture looks like, right? Now, in this case, like I already have a data platform. So I have data coming from all the customer the demographic details. I have the transaction details the customer has done in the past, in the history. There is like campaign data of the customer, like what are the campaign that we had given the customer in the past and the customer has taken it. There is an call center and chat data. The reason sometimes what happened, a customer might not be able to check out. So he might call a call center and tell like, okay, I'm having issues. So we want to make sure that the customer had issues with checking out. We don't want to take that cases and model that. So we have like call center and chat data. All this data goes on daily basis at the end of the day into an centralized data store. It can be your data lake, it can be your data warehouse, or it can be any data store. Now, this is where the data collection challenge comes into play, because you have now data federated across multiple sources, multiple type. Your customer can be a mainframe file, or your transaction can be a mainframe file. Your campaign can be a separate like kind of a data management platform that is available over there, or typical databases. Your call center and chat can be a text data. So there are a lot of factors, but let me focus on the model deployment part. Now, once I have this particular data, what I do is I typically collect my data. I have to kind of join and prepare a data for my particular model. Parallelly, I do data analysis to understand how my data distribution is. Basically, I run some descriptive statistics, I run some inferential statistics, or do some typical exploratory data analysis. And that is input to my data preparation step. The data preparation can be your data cleaning or some kind of rules over there, a transformation rules. And once I have it, I kind of do my feature engineering, right? And these are kind of some features that see all this like it's a sample example. So just want to talk about like why it's very complex when we start deploying it. So what I do is I kind of have the raw data, that is the actual data that is coming from the system of records over here, the customer transaction. And then I have data like I have engineered data. So I have customer 1 to 7 days abandon rates, 7 to 14 days. And similarly, I can have 14 to 30 days, 30 to 60 days. So I'm just trying to generate features so that I can get more insight on why, what is the probability finally the customer might check out, come again and check out. Because sometimes I add to my cart, I walk out, I may come after a few hours and check it out, right? I don't want to just target the customer who have high probability to check out because I don't want like to spend my campaign on those customer where I see high probability of completion of the cart. And similarly, like I have other features as well, like retail. So the idea over here is the top feature that you see are kind of an historical feature about the customer. And the data comes over end of day. And the bottom feature, right, like customer 1 hour average page view time, 3 hours, and current day login count, or maybe did he reopen the cart again today? So these are all like something called real-time features, because I'm or real-time or near real-time. These are all something I'm calculating as it is happening. So I need this information in real time, right? Now, when I'm training my model, all this information is available as history for me. So it's easy for me to take the data and train my model. So once I have these features created, my target column is probability to check out, which will give me a score between like 0 to 1. The higher the score, the more probability the customer is to check out the cart. I train the model, and then I do my model evaluation, hyperparameter selection. I go through this cycle until I get the best model. Now I have the saved model. Like I mentioned some tools, but it can be any tools. It can be Spark ML, it can be scikit-learn, it can be TensorFlow. Let's forget the tool, but in this case, I am give a scikit-learn. I have a saved model, right? And this is the model, right? Basically, I have it in a pickle format. I have the model. But now when I'm deploying, it's not only the model, because I have the entire engineering pipeline from data collection to data preparation to feature engineering that I need to replicate, so that I can do a prediction on the instance. It's not the bundled model might not have all this information, right? Like some of the things you can serialize, like scikit-learn as scikit-learn pipelines. You can serialize your imputer, you can serialize your scaler, but you cannot do a lot of feature engineering work over there that you can do. So a lot of rules, a lot of logic will be outside of your model, right? Now you need to take all this logic. So this is basically the model training pipeline. Now, I spoke about the business objective, but what is my technical objective? So this is one part where many miss to capture during the training cycle or during the problem framing cycle. So now, since it's a very large retailer, right, they have around 100 million customers. Because when I'm deploying my model, as I said, my model becomes a software engineering problem. I need to think about monitoring. I need to think about scaling. I need to think about a lot of other factors from the silicon that I am going to use, whether CPU, GPUs, and from the infrastructure side of it, right? So that's where my non-functional requirements come into play. So in order for me to deploy the model and make it successful, now one thing is, if you see on the back, the training cycle is a cost cycle. So the business does not get any benefit out of it. It's a complete cost. If you're spending 1 year to develop your model, the 1 year is a pure cost. There is no business value generated unless your model is deployed and integrated with your business process. So I have 1 million websites per day. Sorry, the peak daily volume I need to support is 500 transactions per second. That is in parallel. Every second I will get 500 transactions. And during the holiday season or during some say like Amazon as Prime Day, like you will get around 1000 TPS during holidays. or doing Thanksgiving and other season. And the time I have to score is 20 millisecond, less than 20 millisecond, because when a customer re-logs in, I want to tell, okay, you have a cart that is open, and some of the product prices have been dropped. Do you want to check it out now? Or we are giving you a free shipping. Do you want to take it and check it out now? We want to prompt the customer with targeted offers so that the customer can complete their journey, right? And there's also a batch scoring, because not every customer will come and reopen their web page. So for those customers, we want to send an email telling that, okay, you are some unchecked out cart. Do you want to go and complete it? So I have to do a batch scoring also. And I need pretty high availability. Now, if you take typical retail website, it's not only this model, right? You will have their recommendation, their probable product to purchase. So a lot of things get loaded when you log into any site, and everything is a microservice over there. And this is going to be just one of the microservices. And that's why the 20 millisecond response time. So I have 99.95% availability, and I need like near zero downtime. So my application should be able to be always up and predict the outcome, right? So that is my non-functional requirement. Now let's think from this. I have 20 millisecond to do everything. I need real time. So once the real time component comes into play, your sources have changed. Your sources are no longer your enterprise data store. It's going to be a web application. The web application does not have all the historical data of the customer that is required for me to take the data and predict it, right? So what happens? We have to reimagine our pipeline, right? This is how the pipeline looks like. Now, okay, now I need 20 millisecond of response time. So I need to have the data from my enterprise data store. I need to pre-engineer the features. I cannot do it in my pipeline that was done during the training time. In the training time, I will have my pipelines over here that will take the raw data and then create this feature. So I have to pre-compile these features. So I go into an in-memory store or a NoSQL store. Whichever is faster for me. It can be relational database also. It all depends on your volume, your latency. A lot of factors come into play. Now it becomes like an architecture decision that you need to make on what kind of deployment architecture you need. And that's what we are going to build now. We are going to build a deployment architecture. What we saw in the previous slide was a training architecture. And as I said, training architecture is a complete cost to the company. Only once you deploy it, you're going to generate business value out of it. Now, in my in-memory NoSQL store, what I'm doing is I am pre-calculating this data, all this data like customer 1 to 7 days abandon rate, 7 to 14 days abandon rate, customer lifetime value, retail, and all this I'm pre-calculating it, and I'm doing an ETL work and then putting into an in-memory store. Now, I also have real-time data. The real-time data, what I do is as and when the customer log in, maybe I have a streaming pipeline over there. I push the message to a Kafka layer, and from Kafka I read it and put it into an in-memory store, right? I also need other information, whether the customer accepted the offer or not. The reason is if he has not accepted the offer, then I need to build the intelligence in my maybe batch cycle that, okay, this customer was presented an offer, but he has not taken it. Maybe we need to change the offer. There's no point in sending the other offer again and again. So that's why I need to capture the other information also real time as it happens. Now, if you see over here, your entire model pipeline that you built during your training process has changed now. Now you have one more layer, and what happens, it typically becomes on the top, what we thought is we can just take the model, flask it and deploy it, but what in reality as it has become a data engineering and software engineering problem, right? And that's not all, it's just the starting of it. So basically it become a data engineering problem because you have to pre-build these aggregates on a daily basis. You need to also capture the data in real time and put it. It has become a software engineering problem because we are changing the entire pipeline. Now, whatever the data scientist has developed, we are kind of going and changing the entire pipeline and rebuilding the pipeline. And that is what we call as training deployment skew. Typically, a data scientist and software engineering in many cases. In some cases, it will be as easy as just putting the models in Flask. But typically, the real world enterprise, the data is federated. The data collection is a challenge. And you might have heard this, everyone saying that data collection is a major challenge. That's why people build data lakes and data warehouses. So you are basically having a separate code path. Your data scientists have a separate code path. Your software engineering has a code path. And the reason you saw in the previous one, It all depends on your non-functional requirements on how you want to do it. If you just wanted to run it in a batch, then you don't have much of change, right? If you want to do it in real time, then your architecture changes. And now what I am having is, okay, I am having an offline process that is populating it, my NoSQL platform, and then my input is no longer an enterprise data warehouse. My input will be a web interface, and maybe for this purpose, I am just doing a REST API. It can be any other mode of connection also. It can be an gRPC, it can be an streaming pipeline. So I have a REST API now. I collect my data, I prepare my data still, and then I refer to my in-memory NoSQL database for additional data. Because when I get the data from the input, I will just get the customer ID or some customer details. I may not have his historical data. The historical data is what we have built in the in-memory or NoSQL platform. Then I pick my data that I have engineered already, and then I am having a serving interface. Because I no longer, my training is gone, I have a serving interface, I load the model and then start predicting it, right? So that is one of the challenges. But what happens now? Since the data scientist and software engineer have a separate code path, when I go into one more problem, and I need to test this interface completely. I need to test my load from enterprise data store to in-memory NoSQL. I need to make sure the features I am generating are exactly the same value as the training pipeline, right? So that is, you go to the training pipeline, you compare it with your engineered pipeline. You are doing a functionality testing on the final score that is generated, the distribution of score that is generated. So you're going to go and compare. It's a pretty tedious cycle. Because if you have 1,000 features that you have engineered, you have to do it for each and every feature. Even if one feature is kind of during the conversion process is done wrongly, you may end up the entire score getting mismatched, right? So you are ending up in a functionality testing problem, all right? So that's what, if you see over here, now you are in reality, it has become a data engineering problem, it has become a software engineering problem, it has also become an functionality testing problem, right? Now that's not all, right? These are like something which can be done. Now, if you see over here, if you see on the top, the NFR requirement, yeah. So this is the NFR requirement that I had given, right? Like we need an NFR, the non-functional requirements that I stated before. I need less than 20 millisecond response time, and I need to support for 1,000 transactions per second. And this is the availability of it, right? Now, if you see over here, in order for me to run the entire pipeline in 20 milliseconds, I need to know like how my infrastructure is going to look like, how many instances of this model I need, right? I can have it on a single system, but my single system cannot support much. The reason is there are a lot of factors come into play in the infrastructure. Your CPU availability, your memory availability, your bandwidth, your network, your back buffering. There are multiple concepts that come into play. So what I do is I start my performance testing. I pass 1 user, 10 user, 100 user, 1,000 user, and I start benchmarking it, right? Like what is the right number of users a single instance of my model can support, right? Now, what are the typical bottleneck that can happen when your system that you are running on can be a shared resource? So your CPU, memory, bandwidth can be shared. So you need to see like with the shared resource, how much it can come, right? You can go for dedicated resource also, but as you go into more dedicated resource, it will be high cost to the overall project. So you need to see like, because your cost plays an important factor. If you're running the model in Java, then you end up in garbage collections, because as and when there are huge spikes of garbage collections, your system might tend to slow down. There can be a network bottleneck. Think about 1,000 users coming at the same time. The network may not be able to support all of them. Either it will time out or it will throttle the request. There are a lot of this resource bottleneck that comes into play. And that is the reason you go back and check one instance of my model supports how many users in parallel, right? And then now what is happening? My model reality is, okay, I have to do my load and performance testing, right? And these are all cycles that we need to go through. And these cycles can be sometimes take a week or even month. Because you need to go back, if you're not able to meet the 20 millisecond SLA, you have to go back and fine tune your pipeline and come back and do the testing again. And this is just an example. This is pretty common scenario if you're talking for fraud detection, anti-money laundering, or insurance claims. There are a lot of pipelines have this kind of behavior. It is not like one-off pipeline. I would say a lot of real-world industry use cases where the business value is generated today, the pipelines are very complex. The reason is the data is federated, right? Now, this is there, right? Now, okay, now I am done with my load testing, I'm done with my performance testing. Now is the time I go and say, okay, now I have all of this, let me put it in a Flask application, right? And I need to think about scaling now, because based on my performance test, I need to think like how to scale my model. Now what I do is I take this particular Flask application. Now Flask is by default a single-threaded application. It is the inbuilt server is not production ready. Now you can do threading in Flask, but the inbuilt server is not production ready. So you want to go and take the Flask application, bundle it with Gunicorn, and use Nginx for load balancing and back buffering. Right. So I take this. Now I have to decide whether I need to put it in a virtual machine or containerize it. Right. I'm going to tell like what is the difference between both. Now, if you see when I this with virtual machine, when I do a virtual machine, what I can do is I can have multiple instances of my application. Each will be running in one virtual machine because I need to support 1,000 transactions per second. And I decided that, okay, one instance of a model will support only 250 transactions to meet the 20 millisecond SLA. So I have decided, okay, I need 4 instances. Now I have Nginx. I can create a load balancers over there within Nginx. Nginx can act as a load balancer, and then I can call 2 instances in that. Similarly, I can have one more Nginx and I can call 2. The reason you have multiple, if this Nginx fail, then this Nginx should be able to support the volume. So I can create multiple 4 instances or 5 instances. Now, in order for me to load balance it, I can have Nginx itself set up as high availability, or I can have a separate hardware load balancer to do that. Now, the architecture discussion can be anything. Now, the problem with this is I cannot scale up and scale down. My architecture is fixed now. Now, if I want to kind of add one more instance, then I need to go to the Nginx config and then add that particular server to load balance, right? That's the reason we typically prefer container, because Kubernetes is very good. You can just put the containers in Kubernetes and scale it up and down. So during the normal day, you just need 500 TPS. I can run 2 or 3 instances. On a peak day, if it's 1,000 TPS, I can quickly have Kubernetes scale up to support that volume. So the other option is what I do is now scaling. I kind of containerize the application, each and every application. When I'm containerizing it, I don't need Nginx. But even if you have it, it can act as a back buffering over that. You can directly have Gunicorn and Flask application. But it's good to have Nginx, but not really mandatory. Now I can have Kubernetes schedule my different containers in pods, and then I can scale it. Right? Kubernetes also gives other advantage, which I will talk when it come to that point of it. Okay, now I know what has happened. There is a new problem that is at infrastructure, because as I want to scale more, as I want to support more latency, more availability, right? In this case, if I want to support high availability, I can have this Kubernetes in multiple data centers, and I can automatically load balance it, right? So I am getting into infrastructure problem. I need to think about all the infrastructure cost, infrastructure provisioning, and other aspects of it. There are multiple other factors comes into play when it comes to infrastructure. I need to decide if it's going to be a bare metal or Kubernetes, or I'm going to deploy it on a cloud. Right now, if the data is sensitive, there are other factors of it. Typically, organizations prefer it to be on-premise. There are some cases it can be on the cloud. Right? Even in on-premise, do I need to go for Kubernetes, or do I need to go for typical virtual machines? Right? Whether I need a CPU or GPU. Now, some of the deep learning models that you use might require GPU for the mathematical calculation it does in some cases to meet this low latency again. Right, it will work on CPU as well, but to meet your latency requirement, you might need GPU. You need to decide on number of servers required to scale to the peak volume. How many servers do I need? Do I need 5 servers, 10 servers, 20 servers? How many cores I need per server? Now, there is something called core starvation. Now, if you pass too many requests to a single CPU, and the CPU cores will be literally waiting, and that wait can be more than what your SLA is. The wait can be 30 millisecond, but your SLA is 20 millisecond. So that itself can cause problem. If I need high availability and disaster recovery, how do I set my infrastructure in active or active passive? So all these factors that come into play when you are deploying a model in a real world application. Think of like a credit card fraud detection. Now, when somebody swipes a credit card, I want to detect whether the transaction is fraud or not. And if you typically see, as soon as you swipe your credit card, you get an approval or rejected information. The latency is pretty less. You don't want your basically model to fail at that time. You need a model that is highly available all the time, right? So that's where the infrastructure is very key over there. And sometimes in some application, you remember the infrastructure cost can play very key factor, and it can be more than what your training cost is. That's a reality, right? Now we saw basically your all this thing, what we thought on whether it's a Flask or some other problem, it became like a data engineering, software engineering, functionality testing problem, load performance testing, infrastructure. And now you need to replicate, you need to reproduce your output. When I say reproduce, say you are testing in the lower region, you have no containers. The containers will have your package dependencies. Python, you may use pandas, you may use TensorFlow, you may use scikit-learn. Now, scikit-learn will have some NumPy dependency, will have some other version of dependency. All this dependency have to be managed in all the region. You cannot tell, okay, it's working in the development, it's not working in the production. The reason is some package is much. So you need to reproduce it. You need to have a proper CI/CD pipeline setup. So you need to, and as I said, like your deployment problem is a software engineering problem, right? Not really an experimentation problem. You need to have your container Docker file ready. You need to have your Kubernetes scaling script ready. And you need to make sure that, okay, you need to have your Jenkins job that runs, create containers, and deploy it on different environments so that you can reproduce the output. And so it becomes like an CI/CD problem at this stage, right? So now we have deployed it in production. It's kind of running fine, right? I see a lot of questions coming in. Let me take the question towards the end of it, right? What is the square gray box appearing in the top right of the screen? I'm not sure what is it. Okay, I will talk. I'm not saying any gray screen, but let me go and ask for the specific thing. So let me take this Q&A towards the end. So now you have the CI/CD pipeline, but now I have deployed the model. Now, one thing you think, like after the model deployed, that's where your real problem starts, right? Because your model can basically deteriorate as soon. You need to monitor your model. Your model performance can deteriorate as soon as you put your model into production. Your model was maybe trained with the data that was 4 months old, and your customer pattern has completely changed. And typically happens in the fraud world, right? Like as new fraud mechanism and fraud techniques are getting developed, the fraudsters are also like innovating on how to commit fraud, right? So basically your fraud pattern keeps on changing. And similarly, in any business process, the business process is not stationary. So your model may deteriorate. So as soon as you deploy your model in the training, you may got 95% accuracy or recall or precision, whatever model metrics you have. But once you deploy it, it may not even give you like 70% or 60%. So you need to start monitoring your model, right? And for that, what you do, you go back to your training process. In the training process, you have the training data, you have the test data. You feel this model is pretty good. You generate your data distribution statistics, and then you create your model score distribution statistics. That is for the model, what is the score distribution? How much of my model are predicted 0.9 to 0.99% probability? How much of my model are predicted 0.8 to 0.9 probability, right? So basically you're creating a model score distribution statistics. You're creating the data distribution statistics of key variables. Now, if a model has 100 variables, but out of that, my top 15 variables based on the featured importance are contributing to 95% of the outcome. I want to get that data distribution statistics because any change in the top 15 variables can impact my output model severely. Now, the data can be corrupted from source itself, or something could have happened in the ETL process that we are creating. right? So there can be a lot of human error that can happen, that can be data error that can happen. So I need to keep on monitoring my model, or my real business scenario has changed, that my data distribution itself is changing. That those are pretty common. So once I have the statistics, what I do is I take my deployed model. These are the one over here are my benchmark distribution, right? And the what I do is, as and when my model scores, yeah, in frequent interval, I collect my real world distribution, and then I compare it. I make sure my benchmark distribution is equal to the real world distribution or closer to it. But if it is not, that means our model is not predicting properly. So I need to go and retrain my model. So what I do is I go and retrain my model. Now I have to kind of deploy the model as my application is like, I need high availability, right? And that's where a deployment pattern comes into play, right? So this is how your architecture looks like before going to the deployment pattern. Now whatever you saw on the top, your data collection, data preparation, feature engineering, serving interface, saved model, your in-memory SQL. Now, if you see over here, your model monitoring component. The model monitoring component is something you are getting the output frequently, you are comparing it, storing it in the NoSQL and showing dashboard, alerting it, okay, my model have deteriorated, go and retrain the model and deploy a new one. Or maybe stop the model and switch on to a old rule-based system. So you're showing a KPIs in your dashboard, right? So showing like the business KPI, how many cart abandonment did I stop, or the model KPI, how well my model is performing. So this is pretty key, because a lot of people miss the model monitoring part of it, assuming that model deployment is the final step into my production. No, model deployment is just the beginning of a bigger problem that may come. We need to keep on monitoring it. We cannot, if we do a wrong prediction in some cases, right? If my say like a customer is kind of having some fraud issue, and we tell, okay, it's not a fraud. Think about it. You are losing the customer experience. Customer is key to any business, right? So you need to make sure your models are monitored in this world. Like, so that's where like model monitoring comes into play. Now your architecture is becoming complex, right? Not only that, let's talk about the deployment part. The model monitoring is one which I have added over here, which is one more thing we need to take care during the model deployment process. Now the deployment I spoke about, I have a new version of model. Currently, my production is running model version 1, right? And my users are kind of this image I've taken from this source. So it's serving the model. Now what has happened? I develop a new model because my model has deteriorated. I have a new version 2. So I go into something called a blue-green deployment. If you think Kubernetes by default supports blue-green deployment, you just want to make sure you don't like impact the current model. You don't take a downtime. Typically, what we do is we take a downtime and then we kind of override the model, restart it. But in this case, what I'm doing is I'm creating one more copy of the new version of model, and then I am immediately switching over my traffic from model 1 to model 2. And this is called blue-green deployment. But there can be other cases of deployment also. In some cases, I want to do a champion challenger deployment. The reason is, even though I have a new model, I don't want to put it into production immediately. I want to keep it in a challenger mode and then keep monitoring. Maybe 90% of the traffic I want to give to model 1 and 10% of the traffic I want to give to the new model, so that I can monitor how my new model is performing. So that's why the champion challenger deployment comes into play. Right. So now what is happening? Basically, you are getting into a major problem of MLOps. Now, MLOps is again a term coined by all the marketing companies to sell their product, but think it's like a DevOps for ML, right? Now, just 1 minute. My mouse fell down. Yeah. So now you are getting into an MLOps problem, right? Now, if you see over here, your architecture, you have your MLOps also as part of it, because MLOps covers your model monitoring, your model management, your model deployment, retraining, multiple aspects of it. I also need to monitor overall my application and infrastructure. The reason is, if something happens to my infrastructure, I may again have some kind of bottleneck to serve my request. So I also need to keep monitoring my infrastructure. I need to keep monitoring my model. So your model deployment is a constitution of all this thing in real world. Now, how do we do it? That's a story by itself, right? Now, do I build capabilities? Do I build project by project? There are a lot of factors come into play, which I will talk about it. Now, this is what your model deployment challenge are. Right? Now, if you see, there is a very nice article by some of the Google. It's a pretty old article as well called Hidden Technical Debt in Machine Learning System. What we tend to typically focus on is the small box over there, ML code. But if you see, the real challenge is different. The data collection, the serving infrastructure is what we spoke about. Infrastructure is a key component. Monitoring is a key component. Machine resource management is a very key component. So when we talk about model deployment, we have to think ground up from the silicon. When I say silicon, your all the silicon chips like GPUs, TPUs, then comes to your infrastructure, then comes your capabilities that you're monitoring, and finally comes your model part of it. So that's the reason, like sometimes people say, right, like model development is very hard, but model deployment is even harder in a lot of business process. And in some cases, you can develop your model in 3 months to 4 months. Some cases, I'm not generalizing it. In the model deployment can take even months. And that is the reason, that is one of the main reason like model deployment fails to deliver in a lot of times, right? And most of the industry is having challenge with. Now let's talk about deployment model. We just spoke about that. That's about all the challenges and what are the things you need to look at, right? Just a minute. Let me quickly check the time. I have 20 more minutes. So now let's talk about the deployment pattern, right? Now, when we talk about model deployment pattern, like this is how it looks like. You will have like an batch deployment pattern. In a lot of cases, your recommendation engine are typically like pre-built on a nightly cycle and then kept it, right? Or it can be other cases where if you take in the financial industry, you generate your risk reports. You can run your model on a nightly cycle or a weekly cycle for all the customers. You may have 100 million customers. You can just run them in nightly and then you can give it. In this case, the training and the deployment will not have a lot of skew. They are almost identical, and you will see that's why the deployment pattern, I have grouped it from simple to hard over here. So your batch is one part of it. Your near real time is where you don't have very low latency. You can even respond back in 1 second or 2 seconds. Think a customer submits an application for an credit card or submits an application for a bank account, and you want to run models to check whether I can give him a credit card. If I can give him a credit card, what is the credit limit I can give? So I need to run multiple models. One is to see whether the customer information is genuine, the customer is not a fraud, the customer, what I need to run a pricing model to see what is the best limit I can give for the customer. So these are all near real time. The customer submits the application and can wait for 2 seconds or 3 seconds or 4 seconds. But in some cases, you need very real time information. The one we spoke about is like maybe when you want to display and personalized offer on your web page, or it can be when you swipe a credit card, you want to know immediately whether the transaction can be approved or rejected. Because once you approve the transaction, it's very difficult to recover the money, right? There is a big, huge process to recover the money. And finally, you have the edge detection. Now, what is edge detection, right? Now, you have some models. You might want to deploy the model inside an machinery or inside a mobile phone or inside some devices which are running in low computing and low power environment. Now, some of your models are pretty large and heavy. It requires like good compute. Like typically, if you take even a simple TensorFlow model for image classification, the size might run into GB. But if you take a device like mobile, you may not have a lot of memory and a lot of CPU to process it, right? You don't get like 96 core CPUs phone, or you don't get a GPU that often in a phone. So you need to change, you need to kind of, there are techniques to make your model very simple. Most of the model that by default comes with floating point weights. Like if you take your deep learning model, it's nothing but a bunch of weights and biases, right? If you have like 5 layers, each layer will have its own weights and biases. It's a linear equation. Then you have a non-linearity component like ReLU or something like that. Then you take that and again do a matrix multiplication. You do that every layer, right? So what you can do is each and every weight component of it is nothing but a floating point number. There is a concept called model quantization that can reduce your model from floating point to integer point. And once it's reduced from floating point to integer point, your model size reduces, and even the complexity of execution also reduces. So for edge, you may have to do additional scenarios, right? That's what I'm talking about, right? Like if you see, as you go into the harder part of it, you need to maybe in some cases even convert to a different language altogether. Maybe you have developed a model in Python, but I want to deploy this model in a mainframe system. And the mainframe system, I ask like, say like, I need to do it in more like COBOL to meet that particular SLA. So I need to understand my model. If it is an typical regression model, it is nothing but a simple equation that you are taking. You are just taking the coefficients, multiplying by the input value, and then you are kind of adding the bias to it. But if it is a decision tree model, you are taking the model output and converting it to an if-else logic. If it's an TensorFlow model, or if it's a deep learning model rather, then you are multiplying multiple layers of weights to get the output. So you may have to, in some rare, very rare cases, you may have to convert the output into a target language, right? And that's where like the complexity increases as you tend to deploy it. So this is also one of the key factor, right? Like and today more and more models are happening in real-time streaming and real-time environment, and even edge, right? Your fridges or your other machineries, equipment in industry, everything comes with a sensor fitted to it that generates data. Take self-driving car, right? Like that's the, so you need to, if you see a pedestrian, you need to immediately know it's a pedestrian so that you can brake the car. So all these things like that you deploy on the edge of a device need to be pretty work on the constraints of the environment, like the low power and low computing environment. You cannot really go and fit like a tens and twenties of GPUs inside a car and make the car bulky, right? And you need to have lesser electronic part as well. You don't want to get into too many failure bottleneck, right? So that's the deployment pattern. Now, what are the best practices? Right. So here are some best practices. I want to take some time for the Q&A because I can keep continuing, but I will stop after this. So one thing is like, when you are defining your business, a lot of time your model deployment is an afterthought. So once your data scientist is working in complete silos, he talks to the business, he builds the model, he may even like kind of stack 10, 20 models together to get the accuracy. There are a lot of factors that come into play. So involve your data engineers and software engineer during the business formulation and business framing cycle. You need to get your non-functional requirement, your integration touch point with the business process as soon as you start developing the model, right? Because you can start working in parallel. So and also the software engineers and data engineer can build their pipelines in such a way that the model can be easily deployed. And even the data scientists are made aware of the constraints of deploying this model to beat the non-functional requirements. First is you make sure at the beginning of the process, your software engineers, your data engineers, and your machine learning engineers and your business come together and understand the kind of constraints the model will be deployed in. That is the first and second point. Keep your model as simple as possible and as long as possible, right? That's what say, like you don't need to always start with the very complex model for your problem. Yes, if you are doing an image classification problem, maybe a convolutional neural network is the simple model. If you are doing an text classification, it can work with typical machine learning in some cases, but maybe a LSTM may be a simple model. But don't take it to the maximum extreme every time. Always start with a simple model, see how the simple model works, and say your simple model, if it gives like 92% accuracy, and a complex model which you stack with 5 different models gives you 94% accuracy, you need to take a call whether you want to deploy a model with 92% accuracy, you are okay for the extra 2%, or you want to deploy with 94% accuracy, which is stacked model. Now think about a stacked model. Go back to the previous slide where I spoke about the constraints. Now, if you have stacked model, for each of the model, you need to do your performance testing, you need to do your load testing, you need to have your CICD pipeline, you need to have your model monitoring pipeline, and you need to have all the framework set up. And it's going to take, like if you have 5 models, it's going to take 5x the effort. So make sure that your models are simple. In real world, maybe avoid stacking if you can. But in some cases where your accuracy is key, you can do it, but that comes with a deployment challenge as well, understand it. right? So that's what here it is, balance between your performance and simplicity. So if you're not getting too high of a lift, say your simple model is giving 70% and your complex model is given 90%, then it makes sense to deploy a complex model and take the headache. But if it's just a slight variation of it, and if you can substantiate your simple model with additional rules for that mismatch, then go with the simple model. Plan for your infrastructure. Infrastructure plays a very key part both in the training and the deployment. People think the infrastructure is only a training problem. No, it's a deployment problem as well. So plan for your infrastructure at a very early stage of the project and start building capabilities. Like, see, if you're an organization, you are not going to build only one model. You are going to build 10 models or 20 models, or over a time you'll keep building models for different business process. So start with building cross-project capability. So what I call this as a horizontal capability. You will have a lot of use cases that comes in, but your capabilities like your model monitoring, CICD, or model retraining, or feature store, where the in-memory NoSQL I spoke about can be your typical feature store. Plan that very early, plan that cross capability so that it can be used across projects. So that's about it. Let me go to the Q&A and like maybe answer the Q&A session. I'm not sure which gray box. Maybe that was my video which I moved it to the top, right? New model deployment is a very frequent process in user company. See, this new model deployment, right? Typically, you don't keep learning in real time in most of the cases. The reason is your model has to go through multiple model validation cycle and everything, right? So typically what you do, you keep monitoring your model, or you keep retraining your model maybe every month or every quarter. It all depends on your business process. In some business process, like say customer churn, the model might not kind of change so rapidly, like in the case of fraud detection I was talking about. So it all depends on the business process. In some cases, you may have to do like maybe weekly retraining and then deploy it in a challenger mode and test how it is. Or in some cases, you may have to do monthly or quarterly retraining. So it's kind of, it depends on the business process. The online training might be valid in some scenario where you want just some kind of prediction which does not impact anybody, because if I retraining and put the model, there is high possibility the entire model distribution itself can change. While you can do it, but it's a very rare case which can be taken case by case basis, right? What is the frequency of for manual deployment of the cycle shown in the slide title simple model? So the frequency can be as and when you have a model trained, right? You kind of deploy the model, then again you have a retraining model, then you deploy it again. So the frequency also depends on your now in some cases your model will run for years together. In a marketing case, right? Maybe your model might work for 1 or 2 years. You may don't have to retrain and redeploy it. So again, it's similar to my previous question. It all depends on your business process and how your data changes frequently. While fulfilling the objective in slide title is computing and displaying the throughput and probably is computing, and yeah, so when and that's what I talk about, like load performance testing, scaling and everything. Maybe I didn't get this question completely. Maybe if that is the case, yes, it is done. Yes, it is done. Okay. Is model retraining done during near real-time incoming data in a deployed system? Now, the model retraining can be done in near real-time incoming data. So typically what happens, like, let me go back to that slide. That's a good question. So just 1 minute. So if you see over here, what I'm doing is, as and when I am kind of predicting my model, the serving interface, I am also storing the entire output that I used and the score in my offline system, right? And in this offline system, what I can do is I can use this particular environment and I can parallelly run an kind of an auto retraining interface that can create new models and start comparing the output with these particular predictions and see if the model is fine. I can go and deploy it in a challenger mode. So yes, I can do that as well. Again, all this comes with complexity, right? So basically, if your business process really needs it, then do it. If you feel, okay, the model that is that good, I don't want to go through this process of redeploying and everything, then stay away from it, because all this adds to your architecture complexity, all this adds to your deployment complexity. So it has to be taken, like all this architecture decisions have to be taken like case by case basis, right? What is the use of Kafka layer? Because it's the incoming data. So what I am doing is I am just putting it in an kind of streaming platform. It can be Kafka, it can be anything, rather than directly inserting into the database, because I want to decouple my real-time layer with any update to my system to my NoSQL platform. So what I'm telling it to my real-time, because see, I may get 1 million users a day, and the volume will be pretty higher. So I don't want to impact the system. So what I'm telling is, like, as soon as you get the data, just keep putting in a Kafka topic, and I will parallelly read it and upload it, so that I can also keep this as a buffer. If I'm not able to catch up with the data, if my system fails or something like that, the data is still there in Kafka, which I can reprocess it later. Okay. I want to deploy a FAQ model for fetching. How should I deploy? It can be anything. Maybe like I will take this question, I will take some of the questions offline. But yeah, it can be your Flask, or it can be, you need to check what is your interface that you're connecting to, right? If the interface is different, like if the interface, you already have Flask and you already have a well-established environment for deploying it, then go with Flask. But if you want a streaming pipeline, then go with streaming. So it all depends on what you have and what you want to do. Why is GPU training faster than CPU? See, most of the cases, GPU might not, in a typical machine learning problem, GPU might not help, right? But some of the models have been specifically tuned for GPU. Let's take, you have an 100 layer, you have an 5-layer deep learning model, and you have 100 simple neurons, or take in a convolution network, you have filters, right? You have 36 filters. Now, when I run on a CPU, I cannot parallelize all this task. Basically, I have to kind of serialize it and use the CPU memory to buffer this task to my cores. But when I'm running on a GPU, my GPU has thousands and thousands of cores. So I can take this as a matrix multiplication problem, and then just I can push it and get the output. But when I am doing a CPU, even if I do a big matrix multiplication, your CPU will not have that much core. So you end up in keeping CPU memory and then transferring it. And that's the main reason GPUs are faster. And it also depends on the model type, right? Now, if you take XGBoost model, they are also be tuned for GPUs. So you can try to use GPUs, because each tree in XGBoost model, when you are executing, when you are inferencing it during the training, every tree is dependent, because it's an boosting method, right? So your current tree is correcting the error of the previous tree. But when you are deploying it, you can run the tree in parallel, and you can use GPU to speed up that process. So it also depends on the model aspect of it. What is the role called which deployment people play? So the deployment is a combination of your data engineering, which is also your data architecture team, and then your software engineering team. If you are to convert into a target language, if you are going to have like Python or some other framework. So it's a combination of multiple teams. So it's like, yeah, it's a engineering team, architecture team, software team, your IT team, your data scientist team, and also the business team frequently is consulted to know the integration touch point. Yes, the pipeline will differ for different models. It may be simple in case of like simple models, like if you're just taking and let me go to a complete different scenario of your computer vision. Now, if you're just taking an image input, and then you are just predicting whether the image has a cat or dog or anything that is relevant, then your pipeline may be simple. You may do some pre-processing of the image. You may do some kind of maybe truncation or something on the image, some OpenCV, and then you feed the data. But think, if you have multiple things in your pipeline, you need to take the data, you need to detect an particular image from the data, right? Say like if you are running for an semiconductor industry, you want to find if there is any defective chip in that. So you have to detect all the chips in the semiconductor board, and then take that chip and then run your image classification to detect whether that's a defect or not. So the pipeline complexity changes as your problem statement changes, right? So it may differ model to model. And this was just an example that I gave you, but every model might have some kind of complexity in it in real world, right? So SageMaker, see, SageMaker can help you in the deployment, because like if you're using cloud, if you're using Amazon, right, then yes, SageMaker can help you, because it will take the model and deploy it. But outside of SageMaker also, you may run some Amazon EMR jobs or some other Amazon Lambda functions to convert or engineer data. That still you have to manage to deploy it as a pipeline. Now, SageMaker, the model deployment can be one part of it, but your engineering pipeline does not go away. Whatever you do outside of SageMaker, you can run Spark, you can run anything. But when you want to go into a very low latency, you may have to work on converting it, right? But yeah, SageMaker makes it seamless to go from one to another, right? Abhiraj, like, do we have time or how is it?
So you may continue. There's no issue with time.
Okay, let me take a few more questions.
Sure, sir.
Understood around 70% of the things. I don't have anything written. Maybe this recording is available. You can also check. See, some part of this is covered in my. Let me show it to you. In case if you want to check, I have a couple of. Wait, my presentation is moving slowly. So you can check these two particular playlists. I have a set of videos in my YouTube AI engineering channel. One is machine learning model deployment, which covers the theory as well as hands-on, like how to take a Flask model, how to create a Flask model, the best practice of creating a Flask model, how to deploy it in Kubernetes, how to deploy it in a serverless environment. So all these are there. This is specifically for everything, and this also this is taking like a TensorFlow model, which is creating a pipeline and deploying it on Google Cloud Platform. Right here, you will have both serverless and everything. You can check this out. Like it has all the details which I have covered here. Right? Maybe some part are not covered. I will try to cover it. All this recording will be available, which you can use it. How to deal with versioning and hyperparameter tuning of production data. See, like when you talk about versioning, you're talking about model versioning. Now, model versioning, you have predefined MLOps tools that are available, or you can use MLflow or some kind of open source package to do versioning, or you can use Git or any other tool to version your model and then use references of it. Hyperparameter tuning is basically now this when you are like kind of running your model. You first get the right features. You see like what features are contributing. A lot of time will go in your data analysis and exploratory data analysis phase, right? So once you do that, once you know like, okay, I have the right set of features, the very first thing I do is I create a baseline model. The baseline model can be AutoML for you. Just run an AutoML and see which algorithm fits better. You have the algorithms, you take those algorithms and iterate further. And finally, once you say like, oh, I have a decent set of model, let me run an hyperparameter tuning. So I can run like simple random search or grid search or whatever Bayesian search, and then I can do my hyperparameter tuning. So the process is same. Like after hyperparameter tuning, maybe you want to run a cross validation and verify, and finally you select the model or you go back and add more features. There are the cycle keeps on repeating, right? In a percentage accuracy or in terms of time taken. See, the model monitoring performance, it's a nice question. The model monitoring performance is both. Now you need to frequently monitor your model execution performance and model metric performance. So what I spoke about model monitoring is purely model metric performance. So there are techniques to do model metric performance, like your population stability index, your KS divergence. In fact, I have a video on model monitoring talking about technique. You can go and check it. Yeah, so that is one part of it. But you also need to make sure, because your volume might keep on increasing, you want to make sure your model execution performance is not degrading it. Right, so that's where you can use model execution. You can also compare the model execution performance and take a care, right? And MLOps mean this deployment function. It's kind of a deployment as well as management as well as your retraining. So it is more in some cases people use it for training as well. to bring up your containers, to have all the package dependency. But yes, for me, MLOps is your, I would more focus on the operation side of it. But said that, see, these definitions are very, they are not written in stone. People use it to their language or terminology, right? And that's where I will take it like, to me, it's more on the operation side of it. Right? If we can simplify model for edge, why can't we follow the best practice for non-edge? So when you do a model for edge like quantization, the quantization is available only for some of the models. Like you have your TensorFlow models or PyTorch models, you can run quantization. Now, when you are tuning the weight, remember that you are taking your float weight to integer. If you are doing that in XGBoost model manually, then the flow of your if-else condition will change, because there is a loss of accuracy that also comes with your model quantization. Now, for deep learning model, it may not make sense much, but in some of the models are more sensitive to your floating value or to integer value. So it may even completely screw up your model performance. So that's what. See, what I will do is, Abhiraj, if you can share me the questions, maybe I'll try to answer some of the questions offline. Right?
Sure,
I think
Saraj.
there are too
I
many
can share it over
questions.
the mail.
Yeah, yeah. I think that's it. Maybe thank you for joining and staying till the end. I hope this was useful. So I will try to answer most of the questions, whatever come in. I will, because some questions might be common. I can answer it together. So thank you very much again.